Number 13. This is a clever problem or a silly problem or annoying problem, depending on how you look at it. I'm asking you to find the area of the rectangle right here. X runs from 0 to root 3, y runs from 0 to 1. Find the area of this rectangle here using polar coordinates. Of course, we know the area is just going to be square root 3 times 1 is square root 3. We know that. But let's just verify this using polar coordinates. How do we do this? Well, we're going to need to break up our integral. Sorry, we're going to need to break up our area into two chunks, and we'll evaluate two separate integrals here. So there's going to be one calculation to find the area of this triangle down here. There's going to be a second calculation to find the area of that triangle right there. And then we'll add those two areas together. Okay, how to find everything involved in polar coordinates. So for this lower right triangle here, let's see. The bound right here is x is equal to square root 3. What's that in polar coordinates? Well, x is r cosine theta. So r is square root 3 over cosine theta, or it's square root 3 times secant theta if you prefer that version. What also we need to figure out what is the theta value here, because we can see this is going to be r runs from 0 to square root 3 secant theta. Theta here, theta is going to run from 0 to this theta value. This theta value here is corresponding to when x is going to equal square root 3 and y is 1. What is the theta value there? Well, we know that tangent theta is y over x. Tangent theta is going to be 1 over square root 3. And this corresponds in the first quadrant to theta is pi over 6. So one of our integrals, we'll use all of this here. How about the other one? So we have the line here, y is equal to 1. Well, y is r sine theta. And so in polar coordinates, this line is r is equal to 1 over sine theta, where 1 is equal to cosecant theta. We already found that this theta value here is pi over 6, so theta runs from pi over 6 to pi over 2. And r will run from 0 to, r will run from 0 to, let's see here, cosecant theta. Okay, so where are we? Integrating area, the integrand is going to be 1. Of course, it's polar coordinates, so we throw in the Jacobian, r. So the lower right triangle here is theta runs from 0 to pi over 6. R runs from 0 to square root 3 secant theta. R dr d theta. The upper left triangle, theta runs from pi over 6 to pi over 2. R runs from 0 to cosecant theta. R dr d theta. Okay, so we'll just evaluate these two integrals here to finish this off. The first one, r integrates r squared over 2. So we have r squared over 2, plug in r from 0 to square root 3 secant theta d theta. So this will be integral from 0 to pi over 6 of, let's see, root 3 secant theta squared. So that would be 3/2 secant squared theta d theta. Antiderivative of secant squared theta is tangent theta. Plug in theta is 0 to pi over 6. So 3/2 times tangent of pi over 6. And tangent of pi over 6 is going to be 1 over square root 3 minus tangent of 0 is 0. And when you simplify this, you get square root 3 over 2. And then we point out this is what we should get, because our overall area should be square root 3. We just found the area of half of it, square root 3 over 2. As for the other integral, pi over 6 to pi over 2, again, antiderivative r will be r squared over 2. Plug in r from 0 to cosecant theta. And so we end up here, pi over 6 to pi over 2. 1/2 cosecant squared theta d theta. Antiderivative of cosecant squared theta is negative cotangent theta. So we plug in from pi over 6 to pi over 2 here. Negative 1/2 times cotangent of pi over 2 is 0. Cotangent of pi over 6 is square root 3. And so this ends up once again as square root 3 over 2. So our final answer here is square root 3 over 2 plus square root 3 over 2 is square root 3, as we should get. So, yeah, you know, this obviously is not the easiest way to do it, but it's something you should be familiar with, and it's reassuring to know that this works.